Okay, think about this for a second. If you're holding something, maybe a pen or even a ball, and you just let go, it falls. Simple.
Right.
Or if you throw it up, it goes up, stops for a tiny moment, and comes right back down. Seems obvious, but what's really going on there?
Well, that's exactly what we're diving into today, especially for Mr. Martin, grade 8 science class. We're looking at the energy hidden inside that simple motion.
And that big question,
Mm-hmm.
why doesn't a bouncing ball, say, ever quite make it back to where it started? It feels like something's lost.
But that's the fascinating part. Science has this fundamental rule, maybe the most important one for energy. It's called the law of conservation of energy.
Conservation of energy. Okay.
And it basically says energy is, well, it's never created and it's never destroyed, ever. It just changes from one type to another.
Never destroyed. But hang on, when I drop that ball and it bounces lower and lower, eventually stopping, it sure looks like the energy disappeared.
It really does look that way, doesn't it? But it's more like the energy got reshuffled. The total amount, the total sum of energy always stays the same.
Always.
Always. What happens is it switches forms. It might be energy of movement, what we call kinetic energy, or stored energy due to height potential energy. Or sometimes it turns into forms that aren't very helpful for bouncing, like heat or even sound.
Okay, so when I think the energy is gone, it's actually just turned into something else, maybe something I didn't notice, like a tiny bit of heat.
Exactly that. It's not lost from the universe, just transformed into a non-useful form for that specific action, like making the ball bounce high again. So our first big takeaway word here is conservation. The total energy is constant. It just changes its appearance.
All right, conservation means the total stays the same. You mentioned it jumps between forms. For something like a ball going up and down, what are the main energy accounts we're dealing with?
Good question. For motion like this, near the Earth's surface, we mainly focus on two key players: kinetic energy, often shortened to KE, and gravitational potential energy, or GPE.
Okay, KE and GPE. Let's take KE first. Kinetic. That sounds like movement.
Precisely. Kinetic energy is the energy something has simply because it's moving. If it has speed, it has KE.
And I guess like a faster object has more KE than a slower one, and a heavier one too.
You got it. KE depends on both mass, how much stuff is in the object, and its speed, or velocity. Increase either one, and you increase the KE.
Is one more important than the other? Mass or speed?
Actually, yes. Speed is much more influential. For those of you who might look at the formula later, it's TE equals 12 m-lot v to 2. See that? V squared.
Velocity squared. So doubling the speed doesn't just double the energy.
It quadruples it. Speed has a huge impact on kinetic energy, way more than mass does, proportionally.
Wow, okay. So KE is energy of motion, heavily influenced by speed. What are the other one? GPE, gravitational potential energy.
GPE is stored energy. It's the energy an object has because of its height above a reference point, usually the ground. Think about lifting a heavy book onto a high shelf.
You have to do work, put energy in to lift it.
Exactly. And that energy you put in is now stored in the book as GPE. It has the potential to fall back down because of gravity.
So the higher you lift it, the more GPE it stores.
That's the core idea. GPE increases with height. The formula, if you're curious, is GPE in Rus m data. G wada h dot. Mass times gravitational strength times height. But the key thing to remember is GPE is energy stored due to height.
Okay, recapping the key words then.
Yeah.
Kinetic energy is energy due to movement, and GPE is energy stored due to height.
Perfect. Those are our two main energy buckets for this scenario.
Right, now let's put them together. How do they like trade places? Let's go back to throwing that ball straight up.
Okay, so the moment the ball leaves your hand, it's moving fastest. Right?
Yeah, maximum speed just as it leaves.
So that means it has maximum kinetic energy right then. But what starts happening immediately?
Gravity pulls on it, starts slowing down.
It slows down. And as it slows down, its KE is decreasing. But it's gaining height, isn't it?
Yeah, it's going higher.
So that lost KE isn't lost at all. It's being transformed, converted directly into gravitational potential energy. Less speed, but more height.
It's like trading one for the other.
Exactly. Until it reaches the very peak of its flight, that split second where it hangs in the air.
It stops moving upwards for just an instant. No speed.
Right. At that instant, its KE is 0 because it's momentarily still. All the energy it started with is now stored as maximum GPE, maximum height energy.
And then
Gravity wins, it starts to fall, and the whole process reverses. As it loses height, its GPE decreases.
and it picks up speed, so its KE increases.
Perfectly put. GPE converts back into KE all the way down.
That makes sense. It's like a perfect energy swap back and forth, like maybe a sled on a snowy hill, high GPE at the top, low KE, then all KU at the bottom, no GPE.
That's the ideal picture, yes, where all the GPE becomes KE or vice versa. But, and this is a really important but, that perfect 100% conversion only happens in theory.
Theory, meaning not the real world.
Meaning we have to ignore things like air resistance, the air pushing against the ball, and friction. In reality, those things are always there.
Okay, and that brings us right back to the bouncing ball problem from Mr. Martin's class. If I drop a ball from, say, 1 meter high, why doesn't it bounce back up to 1 meter? Where does the perfection break down?
This is where we need our next important concept, efficiency. The energy is still conserved, remember. That initial 1 meter's worth of GPE is all accounted for. But the process of bouncing isn't perfect.
It's not efficient. What does efficiency mean here?
Efficiency is basically a measure of how much of the energy you start with gets converted into the useful form you actually want at the end of a process. We usually state it as a percentage.
Useful, and so for a bounce, the useful energy is the energy that makes it go back up. The energy converted back into GPE, or height.
Exactly. So the ball starts with GPE. Right before it hits the ground, that's pretty much all KE. Then comes the impact, the bounce.
And that's where the inefficiency happens, the imperfect step.
Yes. When the ball hits the floor, it squishes, it deforms, and then it springs back. That whole interaction isn't perfectly elastic. Some energy gets siphoned off.
Siphoned off. Into what? You mentioned heat and sound earlier.
That's right. Two main culprits. First, heat. When the rubber or plastic of the ball squashes and stretches rapidly, there's internal friction. Molecules rub against each other.
And friction causes heat, like rubbing your hands together.
Just like that. It's a tiny amount for one bounce, but the ball and the floor surface get slightly warmer. That thermal energy came from the ball's impact energy, and it's not helping the ball bounce back up.
Okay, so some energy becomes heat. What's the other one?
The sound, that thwack or boing noise you hear,
Yeah.
that's sound energy. Sound is vibrations traveling through the air. Creating those vibrations takes energy, and that energy also comes out of the impact energy budget. The louder the bounce, generally, the more energy was spent making noise instead of height.
So the impact acts like it's sort of energy tax. It takes a percentage of the energy and converts it into heat and sound, which don't help the bounce.
Energy tax, I like that,
Don't
yes.
worry.
If, say, 20% of the energy gets turned into heat and sound during that bounce,
Then only the remaining 80% is left to be converted back into GPE, back into height. So it only bounces 80% as high.
precisely. That's why the bounce is always lower. The efficiency, our key word here, is less than 100%. It tells us how much useful output we got from the input energy.
That makes so much sense now. It's not lost, it's just changing into forms that aren't bounce. Okay, this is great because it connects directly to what the students can actually do in the lab. How can they measure this efficiency?
Yeah, the bouncing ball experiment is a fantastic hands-on way to see this. You're basically going to measure the efficiency by comparing heights. Since GPE is directly related to height, GPE and G, if the mass M and gravity G stay the same,
Then the height tells you everything you need to know about the GPE.
yeah.
You don't even need to calculate the actual energy in joules.
but for efficiency, nope. You just need the ratio of the heights. It simplifies things a lot. So the basic steps are pretty straightforward. First, you'll choose maybe 5 different starting heights to drop the ball from, like 50 centimeters, 100 centimeters, 150 centimeters. You get the idea.
Okay, 5 different drop heights. That's your initial GPE level for each trial.
Right. Then, for each drop height, you need to carefully measure how high the ball bounces back up. Get down low, eye level with the bounce, maybe have a partner help watch.
And probably do it a few times for each drop height and take an average, right, to be more accurate.
Absolutely. Good science practice. Measure the bounce height accurately that represents the GPE the ball got back after the bounce. Then comes the calculation.
How do you calculate the efficiency percentage from the heights?
It's just a simple ratio. The efficiency is the bounce height divided by the original drop height. Then multiply by 100 to get a percentage.
So if I dropped it from 100 centimeters and it bounced back up to, say, 70 centimeters?
And the efficiency is 100%, which is just 70%. Your ball is 70% efficient for that bounce.
That's simple enough. And what will students likely find if they test the same ball from different drop heights?
Well, usually you'll find that the efficiency percentage stays roughly the same. If your ball is, say, 70% efficient when dropped from 50 centimeters, it'll probably still be around 70% efficient when dropped from 150 centimeters. The material the ball is made of kind of determines its inherent bounciness or efficiency.
Interesting. So the material itself has a characteristic efficiency. Okay, let's quickly summarize the big ideas from this deep dive.
Sounds good. We started with the big one, the law of conservation of energy. Energy isn't created or destroyed, it just transforms.
And we saw that transformation in action, specifically between movement energy, KE, and height energy, GPE.
Then we hit the real world, why things aren't perfect. Bounces aren't 100% efficient because some energy always gets converted into less useful forms, mainly heat and sound during the impact.
Which explains why the bounce height is always less than the drop height. It's all about that efficiency percentage.
Exactly. It's energy accounting, plain and simple.
Okay, now for a final thought. Something for you listeners, especially Mr. Martin's class, to chew on as you work on your experiments and calculations. Think about that link between height and speed again.
Yeah, remember, if you know the starting height and the mass m of your ball,
Yeah.
you can calculate its initial GPE. A Lover Norder's DJAHO. Now, assuming negligible air resistance on the way down,
That starting GPE must equal the maximum kinetic energy the ball has just microseconds before it hits the ground, right? Energy conversion.
right, so now you know the maximum KE, and you know the formula for kinetic energy is TE equals 12 mhe2. You know KE, you know m.
Wait, so you could actually figure out V, the maximum speed the ball reaches.
That's the challenge for you. How could you rearrange that TKE m called V22 formula to solve for $5, the velocity? Knowing the starting height lets you predict the maximum speed. That's the real power of understanding energy conservation and transformation.
Very cool. Connecting height directly to speed using energy. Definitely something to explore. Go see how fast those bouncing balls are really moving.